All right, so here I'm just going to walk through some equations with variables on both sides of the equal sign. And I'm going to specifically focus on special cases. So when I say special cases here, I really mean equations that give us no solution or infinite solutions. Not all of these equations will have special cases or will be special cases, but some of them will have no solution, some will be infinite solutions, and then others where I won't really call these special cases, they will have one solution where x just equals one number. So these special cases really only happen when I have variables on both sides, because the variable term will actually cancel out on both sides. Actually, anytime I have variables on both sides, I want to think about how to combine my variables to one side. So I'm going to think about how do I get all of my variables to this side. You can put them on either side. I'm just going to decide to put them on the left side for now. So how do I combine, how do I basically cancel this term out and bring it over to the other side? So I'm thinking about canceling out a negative 9x, which means I have to add 9x to both sides. That cancels out on the right side, and then on the left side, that would give me 18x. This plus 21 comes down, and that still equals just 21 left on that side. So immediately in that step, I can see that this is not a special case. Special cases really only happen when this variable term cancels out and this variable term cancels out, but that's not what happened there. They combine to make an 18x. Really, they have to be identical on both sides. This is a negative 9x, while that's a positive 9x. So this is not going to be a special case. I'm just going to keep solving that by subtracting 21 on both sides. Since I brought my variable to the left side, that means I'm really bringing my constants all over to my right side. I'm only going to be left with constants on that side, which means I have to cancel out the constant on the left side. So I'm canceling that out by subtracting 21. And if I do it on that side, I also have to do it on this side. So the 18x comes down, and I'm left with just 0 on the right side. Now to finish this, I want to cancel out that multiplying by 18. So I'm going to divide by 18. That cancels out. That gives me x equals 0. That seems like it might be a special case because you got these constants to cancel out, but that really isn't a special case. That is just one solution, and that solution is 0. On the next one, I still have variables on both sides, but before I can combine things from the left and the right side, I just want to combine like terms on this left side. I just want to subtract those two. 2x minus 6x would give me negative 4x. The minus 1 comes down, and that still equals negative 1 minus 4x on the right side. And actually, right in this step, I can tell that I have the exact same expression on the left side and on the right side. I have a negative 4x and a negative 1. I have a negative 1 and a negative 4x. They are identical on the left and right side. So actually, right away, I can tell that this is going to be infinite solutions. It doesn't matter what number I plug in. Whatever this expression equals, it will be the exact same thing on the right side. It doesn't matter what number I plug in for this x. As long as I plug in the same number for that x, these expressions will always be equal to each other. I'm going to finish this just because it's not always that easy to recognize. Sometimes you don't see it right away. But I'm going to basically take the exact same step that I did on the previous problem where I pull all my variables to the left side. So I'm going to cancel out this negative 4x or minus 4x by adding 4x. And then you're going to see that these also cancel out. It cancels out on both sides, leaving us with a negative 1 equal to negative 1. And since that's a true statement, that's another way of seeing that no matter what number I plug in, these variable terms are always going to be the same, and I would get negative 1 equals negative 1. So I have infinitely many solutions. Another way to say that is that I have my solution set is all real numbers. Those are two different ways of basically saying the same thing here. All right, on this one again, I have variables on both sides, but before I want to combine those two, actually let's change colors a little bit. Before I combine those two, I'm going to combine the stuff separately on the left side and then on the right side. So I'm going to just combine like terms on the left. That would give me 7x minus 7. On the right side, that would give me a negative 7 and negative 2. Make sure you include this sign. That's a negative 2 plus 9. That's a positive 7x. So again, you should recognize right here, I have a negative 7 and a negative 7, a positive 7x and a positive 7x. Those are identical. If I were to subtract 7x from both sides, the variable terms cancel out, and I get another true statement. Negative 7 equals, actually I'm going to get rid of that line because that makes it almost seem like they're not equal. Negative 7 equals negative 7. That is a true statement. Whenever you get down to the variables canceling out and the same constant on the left side and the right side, that's telling us that we have infinitely many solutions. Or you can say your solution set is all real numbers. All right, again, variables on both sides. I have a negative 3x by itself on that side, and when I combine like terms here, that will also give me a negative 3x. 6x minus 9x is negative 3x. The minus 11 comes down, and so does this negative 3x on that side. So now I see that I have a negative 3x on the left and on the right side. When I cancel these out, I forgot to change colors. When I cancel these out, when I cancel out that negative 3x, it will also cancel out the negative 3x on this side. I'm imagining bringing my variables to this side while I bring my constants to the other. So I'm going to leave this negative 11x on that side. Sorry, negative 11, no x attached to that. And cancel out this 3x, but it also happens to cancel out this 3x. Negative 3x plus 3x is really 0. This is not a true statement. This is a false statement, which is telling us that we have no solutions. There is no number I could possibly plug in to this. Actually, it's probably easiest to see in that step. I'm going to rewrite that. If I were to plug in some number there and plug in the same exact number here, whatever this equals, this side is going to be 11 less than that. It's taking that number and subtracting 11 from it. It's going to be this number minus 11. These will never be equal to each other. There is no solution here, no number that I can plug in for x to make this equation true. That's why I say I have no solutions. Or your solution set is the empty set. Or you can say no solution in that way with a 0 and a diagonal line through it. This was a little bit trickier just because I have to distribute first, but it's really the same idea. I still have variables on both sides. So I'm imagining, how do I get all of my variables to combine onto one side? Before I do that, I have to multiply this out. I'm going to distribute the 4 into both terms inside the parentheses. 4 times negative 3 is negative 12, and 4 times negative 2x is a negative 8x. So in this step, I know that it's going to be one of the special cases because I see the exact same variable term on the left and the right. I have a negative 8x on the left and a negative 8x on the right. I know those two terms are going to cancel out. I'm going to add 8x to this negative 8x to cancel that out. If I do it on the right side, I have to do it on the left side too. And like I said, those also cancel out. And my constants come down as negative 12 equals positive 12. That is not a true statement. Positive 12 and negative 12 are different. This equation has no solution. All right, this one looks a little bit trickier, but it's really the same kind of steps. I want to think about how to combine everything on one side first. So I'm going to combine stuff just on the left side first, which means I have to distribute and then combine like terms. And I'm kind of going to do the same thing on the right side. Let's just take that one step at a time, though. I'm going to distribute this first. 2 times 4x is 8x. 2 times negative 3 is negative 6. So all I did so far was just distribute on that side. I'm going to do the exact same thing on the right side. I'm going to take that negative 8 and distribute into both terms there. Negative 8 times 2. Actually, sorry, before I do that, I'm going to drag this 4 down and now write that next term. Negative 4 times 2 is negative 16. And negative 4 times a negative 1x is a positive 8x. So right here, I know that my only variables left are a positive and a negative 8x. That's telling me it's going to be a special case. It's either no solution or infinitely many solutions. Because in this next step, I'm going to subtract 8x from both sides. And it cancels out on the right, and it cancels out on the left, giving me just, actually I'm going to combine these in that same step. Sorry, I'm combining too many maybe. But I'm also going to combine like terms here, and I'm going to combine like terms there. Negative 6 minus 6 is negative 12. 4 minus 16 is negative 12. So we can see that the constants ended up as the exact same number on both sides, and the variable terms cancel out. That means I have infinite solutions, or my solution set is all real numbers. Again, you can phrase it either way. One is talking about actually the numbers that describe your solution set. If you were to list out all of the numbers that solve this equation, it would be all real numbers. This more describes how many solutions you have. That is really the key distinction between these two different special cases. Infinitely many solutions is talking about plugging in any number into an equation, and it's always true. No matter what I plug in here, it will always be the same as that. Whereas no solution means that no matter what I plug in here, this will never be equal to that side. This side would always be 1 greater than the left side.